Welcome to CEDA-Labz. First, let's find out the answers to the questions asked in the last tutorial. Our first task was to design two-input NAND gate using gate-level modeling. So, here's how we instantiated NAND gate primitive for designing this gate. And did the same for our second task, to design NOR gate. In third one, we have to design two-input my and my OR and my NOT gates from two-input NAND gate. And this is stimulus block of my OR, stimulus block of my N. And this is stimulus block of my NOT. Next task is to design full adder. Here is the code of full adder using gate-level modeling. This is Module-2, Verilog HDL, Part-3 dealing with data flow level of abstraction. In this tutorial, we will learn data flow modeling, continuous assignment statement, delays in data flow modeling, operator types, and at the end we will use data flow constructs to model practical digital circuits in Verilog. Data flow modeling provides a powerful way to implement a design. Verilog allows a circuit to be designed in terms of the data flow between registers and how a design processes data rather than instantiation of individual gates. Later in this tutorial, the benefits of data flow modeling will become more apparent. Operators act on the operands to produce desired results. Verilog provides various types of operators. Operators can be arithmetic, relational, equality, logical, bitwise, reduction, shift, concatenation, replication and conditional operator. Some of these operators are similar to the operators used in the C programming language. Each operator type is denoted by a symbol. Arithmetic operators. There are two types of arithmetic operators, binary and unary. Binary arithmetic operators are add, subtract, multiply, divide, modulus and power. The operators plus and minus can also work as unary operators. They are used to specify the positive or negative sign of the operand. Unary plus or minus operators have higher precedence than the binary plus or minus operators. Unary operators require only one operand. Modulus operator produces the remainder from the division of two numbers. If any operand bit has a value x, then the result of the entire expression is x. This seems intuitive because if an operand value is not known precisely, the result should be an unknown. Binary operators require two operands. Here are some examples showing use of arithmetic operators. Relational operators are less than, greater than, less than or equal to and greater than or equal to. Relational operators always give result in one bit. If relational operators are used in an expression, the expression returns a logical value of 1 if the expression is true and 0 if the expression is false. If there are any unknown or z bits in the operands, the expression takes a value x. These operators function exactly as the corresponding operators in the C programming language. Here are some examples showing use of relational operators. Here, A and B are 4-bit registers. So, our first example is A is less than B, which is false. Instead, A is greater than B. This is why its result will be 0. Another one is A is greater than 8, and, of course, A is greater than 8. So, it will return 1. Similarly, A is less than equal to B returns 0. And A is greater than equal to B returns 1. Another one is A less than 4-bit 1, ZZZ. It will return X. Why? Because whenever there is any unknown or Z bit in the operand, expression results to an ambiguous state that is X. Some more examples for you. I hope you can answer them. Well, these are the answers. I hope you got the same result. Equality operators are logical equality, logical inequality, case equality, and case inequality. When used in an expression, equality operators return logical value 1 if true and 0 if false. These operators compare the two operands bit by bit, with 0 filling if the operands are of unequal length. It is important to note the difference between the logical equality operators and case equality operators. The logical equality operators will yield an X if either operand has X or Z in its bits. However, the case equality operators compare both operands bit by bit and compare all bits, including X and Z. The result is 1 if the operands match exactly, including X and Z bits. The result is 0 if the operands do not match exactly. Case equality operators never result in an X. Some of the examples are here of equality operators. 2 4-bit register, A and B. Is A equal to 4-bit 1, 1, 0, 0? And, yes it is, that is why it will return 1. Second example is also like this. In third one, A is compared with 4-bit 1Z1, 0. One of the operand contains Z. So, result will be unknown, that is, X. Similar is the case for the fourth one. In fifth example, we are using case equality operator. And as we see, it consists of an unknown bit. But the result is not an X. It is 0. Why? Because of case equality operator. It can compare X and Z bits too, and here, first and third bit does not match. Similarly, in sixth example, result is 0 because first bit does not match. Similar is the case of seventh and eighth example. Some more examples so that the vision is clear. Here, first example is very simple. It is very obvious to have a result, 0, as 4 is not equal to 3. Second one, X is not equal to Y, which is true. So, it will return a 1. Third, is X equal to Z? No, because operand Z contains X and Z bits, and the operator in use is logical equality, which cannot compare X and Z bits. Hence, results in an X. In fourth one, all bits are matching, that is why it is true and returns 1. In fifth one, bit 1 does not match. Hence, it returns 0. And in last one, is M not equal to N? Yes, because LSB does not match. Hence, it is true. Logical operators are mostly used all connect expressions. Logical operators are logical and, logical or, logical not. Operators logical and logical or are binary operators. Operator logical note is a unary operator. Logical operators follow these conditions. Logical operators always evaluate to a 1-bit value, that is, 0 when false, 1 when true, and X when ambiguous. If an operand is not equal to 0, it is equivalent to a logical 1, which is a true condition. If it is equal to 0, it is equivalent to a logical 0, which is false condition. If any operand bit is X or Z, it is equivalent to X, that is, ambiguous condition, and is normally treated by simulators as a false condition. Logical operators take variables or expressions as operands. Use of parentheses to group logical operations is highly recommended to improve readability. Also, the user does not have to remember the precedence of operators. Here are some examples showing usage of logical operators. A is equivalent to logical 1, as it has some value, that is, 3. On the other hand, B is equivalent to logical 0, as it is equal to 0. If we AND logical 1 and logical 0, it results to a 0. Similarly, in second one, A or B, that is, 1 or 0, which is equal to 1. Third one, not A, not of 1 will be 0. Similarly, not B evaluates 1. Another set of register, in this, A is equivalent to X, as it contains unknown bit, and B is equivalent to 1 as it has some value. Hence, if we AND X with anything, it will result to an X. Some more examples of the same. These operators are very simple and easy. I hope it is clear to you now. Bitwise operators perform a bit-by-bit operation on two operands. Bitwise operators are negation, AND, OR, XOR, and XNOR. They take each bit in one operand, and perform the operation with the corresponding bit in the other operand. If one operand is shorter than the other in size, then it will be bit extended with zeros, to match the length of the longer operand. A Z is treated as an X in a bitwise operation. The exception is the unary negation operator, which takes only one operand, and operates on the bits of the single operand. Logic tables for the bit-by-bit computation are shown here. Bitwise, AND, bitwise, OR, bitwise XOR, bitwise XNOR, bitwise negation. Let's just understand the concept of bitwise operators through these examples. Here are two registers, A and B, and we are performing bitwise operation on the two. First one is A and B. As discussed earlier, here Z is treated as X. We will perform bit-by-bit operation. So, according to the logic table, Z, that is, X in one bitwise operation, will yield an X. X in 1 will again result to X. Z in 0 will yield 0. Similarly, X in 0 will give 0. 0 and 1 will give 0, and so on. Some more examples of bitwise operator are also shown here. It is important to distinguish bitwise operators from logical operators. Logical operator always yields a 1-bit logical value, 0 or 1 or X, whereas bitwise operators yield a bit-by-bit value. Logical operators perform a logical operation, not a bit-by-bit operation. Reduction operators are AND, NAND, OR, NOR, XOR, and XNOR. Reduction operators take only one operand. Reduction operators perform a bitwise operation on a single vector operand and yield a 1-bit result. The logic tables for the operators are the same as shown in bitwise operators. The difference is that bitwise operations are on bits from two different operands, whereas reduction operations are on the bits of the same operand. Result is calculated by recursively applying bitwise operation on all bits of the operand from right to left. Reduction NAND, reduction NOR, and reduction XNOR are computed by inverting the result of the reduction NAND, reduction OR, and reduction XOR, respectively. Here's how reduction operator works. In example 1, AND X, first bit 1 and bit 2 is ANDed, that is, 1 and 0, which is equal to 0. Now, the result of first to that is 0 is ANDed with third bit, 0, and 0, which is again 0. Again, following the same procedure, 0 ANDed with the fourth bit, which results to 0. Same is followed by another example. Examples showing usage of reduction operators. Shift operators are right shift and left shift. Regular shift operators shift a vector operand to the right or the left by a specified number of bits. When the bits are shifted, the vacant bit positions are filled with zeros. Shift operators do not wrap around. An example showing how a shift operator works. Some more examples showing use of shift operators. Here, in first example, y is evaluated when x is shifted to left by 1 bit. So, third bit value will be shifted to fourth bit, second bit value will be shifted to third bit, and last bit value will be shifted to second bit, and lastly, vacant position of LSB is filled by 0. Hence, result is 1, 0, 0, 0. Similarly, in second example, x is shifted by 2 bit. Hence, second bit value is shifted to fourth bit, first bit value is shifted to third bit, and remaining vacant positions, second and first one, is filled with zeros. Have a look at all other examples. It is very easy. Shift operators are useful because they allow the designer to model shift operations, shift and add algorithms for multiplication, and other useful operations. The concatenation is expressed by the brace characters, bracketing two or more expressions separated by commas. The concatenation operator provides a mechanism to append multiple operands. Here is the syntax. A concatenation expression can be either an identifier or a sized number. Unsized numbers are illegal, because the size of all operands is required to calculate the size of an entire concatenation. Operands can be scalar nets or registers, vector nets or registers, bit select, part select, or size constants. Concatenation can take any number of operand. Let us have a look at some examples representing concatenation. Here y is concatenation of B and C, where B is 0, 0 and C is 1, 0, and when it is concatenated it appends to 0, 0, 1, 0. So, y is for tick B 0, 0, 1, 0. Similar is the case with second example. In third example, expression third is an unsized number, 3, which is invalid. Repetitive concatenation of the same number can be expressed by using a replication constant. A replication constant specifies how many times to replicate the number inside the brackets. This is the syntax. And here comes the examples. In first one, y is concatenation of 4 times replicated a, where a is 1, and replicated 4 times, so y is 4 bit 1, 1, 1, 1. Similarly, in second one, y is 4 times a, and 2 times b. Isn't this operator very simple? We just have to rewrite the expression, number of times it is mentioned. The conditional operator, that is, question mark and colon, takes 3 operands. This is its syntax. The conditional expression is first evaluated. If the result is true, that is, logical 1, then the true expression is evaluated. If the result is false, that is, logical 0, then the false expression is evaluated. If the result is x, that is, ambiguous, then both true expression and false expression are evaluated and their results are compared, bit by bit, to return for each bit position an x, if the bits are different, and the value of the bits, if they are the same. It is to be noted that conditional operator can be nested. Here is an example of conditional operator. Conditional operators are frequently used in data flow modeling to model conditional assignments. The conditional expression acts as a switching control. Conditional operators can be nested. Each true expression or false expression can itself be a conditional operation. Having discussed the operators, it is now important to discuss operator precedence. If no parentheses are used to separate parts of expressions, Verilog enforces the following precedence. Operators listed in this table are in order from highest precedence to lowest precedence. It is recommended that parentheses be used to separate expressions except in the case of unary operators or when there is no ambiguity. For small circuits, the gate-level modeling approach works very well, because the numbers of gates is limited and the designer can instantiate and connect every gate individually. Also, gate-level modeling is very intuitive to a designer with a basic knowledge of digital logic design. However, in complex designs the number of gates is very large. Thus, designers can design more effectively if they concentrate on implementing the function at a level of abstraction higher than gate level. With gate densities on chips increasing rapidly, data flow modeling has assumed great importance. No longer can companies devote engineering resources to handcrafting entire designs with gates. Data flow modeling has become a popular design approach, as logic synthesis tools have become sophisticated. This approach allows the designer to concentrate on optimizing the circuit in terms of data flow. A continuous assignment is the most basic statement in data flow modeling, used to drive a value onto a net. It allows the use of Boolean logic rather than gate connections. This assignment replaces gates in the description of the circuit, and describes the circuit at a higher level of abstraction. The assignment statement starts with the keyword assign. The syntax of an assign statement is shown here. Continuous assignments are always active. The assignment expression is evaluated as soon as one of the right-hand side operands changes and the value is assigned to the left-hand side net. Continuous assignment statements are concurrent. At any simulation time, all continuous assignment statements that have an event are executed concurrently. The left-hand side of an assignment must always be a scalar or vector net or a concatenation of scalar and vector nets. It cannot be a scalar or vector register. Here is the syntax. The operands on the right-hand side can be registers or nets or function calls. Registers or nets can be scalar or vectors. Continuous assignments provide a way of modeling combinational logic at a higher level of abstraction than gate-level logic. It is best modeling for combinational circuits because of nature of continuous assignment statements, that is, concurrent. These statements are also known as regular assignment statement. This is the default statement for any module. Thus, default data type for any module is net type and default port is also of net type. Instead of declaring a net and then writing a continuous assignment on the net, Verilog provides a shortcut by which a continuous assignment can be placed on a net when it is declared. There can be only one implicit declaration assignment per net, because a net is declared only once. In this example, an implicit continuous assignment is contrasted with a regular continuous assignment. This is a basic example showcasing the use of continuous assignment statement. Another example, in the last tutorial, we modeled half-adder through gate-level modeling. Here we are designing half-adder via data flow modeling. We will start exactly in same way, with keyword, module. Module name is HA_data, followed by port list. Sum, S, and carry, C, is declared as output. An input, A, and B, is declared as input. In gate-level modeling, we used to design our code according to the gate-level diagram. Here we design our code via defining how data flows between the register. As you know, in half-adder, sum is evaluated when we do ORing of two inputs. And carry is evaluated when we do ANDing of two inputs. And in the design code, this relationship is defined using operators. And at the end, module is terminated by the keyword end module. This is the stimulus block for the half-adder. Stimulus block will be the same. As in stimulus block, we provide environment to the design block, which won't be affected if we write our code in gate-level modeling or data flow or behavioral. It would remain the same, except instantiation portion. We would instantiate the design block, which we want to test. This one is the example of full adder using data flow modeling. It is easy to write code in data flow, as we only need to define the relationship of registers. Here is an important note. In first figure, as you can see, the figure is formed when we are using Bitwise Operator. And on the other hand, logical operator will consider the circuit in this form, which is not expected. So we should use operators according to the circuit requirements. Always remember, when we want to describe any circuit, we should use Bitwise Operator, as Bitwise Operator perform bit-by-bit operation. And when we want to check any condition of a circuit, we should use logical operator. Delay values control the time between the change in a right-hand side operand and when the new value is assigned to the left-hand side. Three ways of specifying delay in continuous assignment statement are regular assignment delay, implicit continuous assignment delay, and net declaration delay. The first method is to assign a delay value in a continuous assignment statement. The delay value is specified after the keyword assign. Here is the syntax and an example. Any change in values I1 and I2 shown in example will result in a delay of 10 time units before a computation of the expression I1 and I2, and the result will be assigned to out. If I1 or I2 changes value again before 10 time units, when the result propagates to out, the value of I1 and I2 at the time of recomputation are considered. This property is called inertial delay. An input pulse that is shorter than the delay of the assignment statement does not propagate to the output. This waveform is generated by simulating the example which is discussed in the last slide. It shows the delay on signal out. Note the following change. When signals I1 and I2 go high at time 20, out goes to a high 10 time units later, that is, time equals 30. When I1 goes low at 60, out changes to low at 70. However, I1 changes to high at 80, but it goes down to low before 10 time units have elapsed. Hence, at the time of recomputation, 10 units after time 80, I1 is 0. Thus, out gets the value 0. A pulse of width less than the specified assignment delay is not propagated to the output. Inertial delays also apply to gate delays. An equivalent method is to use an implicit continuous assignment to specify both a delay and an assignment on the net. This example shows the difference between the regular assignment delay and implicit continuous assignment. The declaration above has the same effect as defining a wire route and declaring a continuous assignment on/out. A delay can be specified on a net when it is declared without putting a continuous assignment on the net. If a delay is specified on a net out, then any value change, applied to the net out, is delayed accordingly. Net declaration delays can also be used in gate-level modeling. Both the declarations will have same effect. Here is an example of both net declaration delay and regular assignment delay. In net declaration delay, delay is defined at the time of port declaration only, whereas, in the latter one, delay is defined after the keyword assign. Gate-level modeling of a 4:1 multiplexer is discussed in the last tutorial. The logic diagram for the multiplexer is also given there, and its gate Verilog description was also discussed. We describe the multiplexer using data flow statements. Compare it with the gate-level description. We show two methods to model the multiplexer by using data flow statements. We can use assignment statements instead of gates to model the logic equations of the multiplexer. Notice that everything is the same as the gate-level Verilog description, except that computation of out is done by specifying one logic equation, by using operators, instead of individual gate instantiations. Input-output ports remain the same. This is important so that the interface with the environment does not change. Only the internals of the module change. Notice how concise the description is compared to the gate-level description. There is some more concise way to specify the 4:1 multiplexer. In conditional operator section, we described how a conditional statement corresponds to a multiplexer operation. Convince yourself that this description correctly models a multiplexer by analyzing it again and again. In the simulation of the multiplexer, the gate-level module stimulus module can be substituted with the dataflow multiplexer modules described above. The stimulus module will not change. The simulation results will be identical. By encapsulating functionality inside the module, we can replace the gate-level module with a dataflow module without affecting the other modules in the simulation. This is a very powerful feature of Verilog. Data flow description of a 2-bit comparator. As we know, in digital system, comparison of two numbers is an arithmetic operation that determines if one number is greater than, equal to, or less than the other number. So comparator is used for this purpose. So we declare 3 outputs and 2 inputs of 2-bit, as we are designing 2-bit comparator. Using operators, we define this relationship. First one is for A is greater than B. If it is true, it will return 1 or else 0. Similar is the case for the rest of 2. Always remember, before writing any code, you should have understanding of functionality of the required circuit. Come on, let's move into the flashback. So far we learned about next level of abstraction, that is, data flow modeling. One of the main construct used in data flow modeling is continuous assignment statement. Another kind of statement, which is called as implicit continuous assignment statement. We learned different kind of operators: arithmetic, logical, relational, equality, bitwise, reduction, shift, concatenation, replication, and conditional. We studied 3 types of delay in data flow modeling: regular assignment delay, implicit continuous assignment delay, and net declaration delay. Then we did some examples in data flow modeling using its concepts and operators we studied so far. Some questions for you. I hope you'll be able to answer them.